Hello. Before I start, I just want to say that I apologize for my pronunciation of Routh Hurwitz criteria. Before we go into the video, I won't be saying it a lot, so hopefully I won't annoy you with that. Okay, let's get started. This video is going to be about stability of systems. Whenever you want to design any control systems, the three things that come into your mind are the transient response of the system. So there's a transient response of the system. Then the second thing that should come into your mind is there's the transient response. The second thing that should come into your mind is the stability of the response. And the third thing that should come into your mind is the steady state error. The key aspects that should be in your mind whenever you think about designing a control system. Now, today we discussed stability. Now, I won't be going into analyzing the Routh table, but I will tell you how to make one. So let me just select my pen here. Let me make sure that all the settings are set. Good, and okay, we are set to go. Closing this. Okay, so when you have a closed loop system, so you have something like this. Here is your transfer function, and here is your output. Let's call the output C of S. So we are in the Laplace domain, and let's call our input, R of S. This is our input, and let's have an adder here. And let's subtract from this. Okay. When we have, this is our forward transfer function, okay, so whatever comes here goes straight here. Then this is our feedback loop. Now, you probably don't know, but the total transfer function of the whole system, that is including the feedback and including the forward transfer function, turns out to be, so it becomes T of S on 1 plus minus G of S, so G of S, H of S, where H is your feedback transfer function. Now in this case, that is just 1. So you get the idea, and G of S is equal to T of S in this case. So that's how that works out. So when you solve for that, you can solve for this and come up with the whole system transfer function. So you can pretty much write this system. You can write this system over here, that is this system over here, as this. I'm just gonna R of S and just one block, and then one block is going to look something like this: 1 plus minus G of S, H of S, and in this case H of S is equal to 1 because we are just taking 1 back here. Okay, now I'll just get rid of this and let's move forward. When we do that, often you will see that we come up with complex transfer functions. So for example, I'm going to choose a different color. Let's choose blue. Let's choose blue, okay? So let's take this transfer function. So we have some R of S, and let me just draw some error here. And we have this transfer function here, which is 3 on S, S plus 1, S plus 2. And we have our output here, so output is going to be something like C of S, and I'm going to have unity feedback here. Okay, now if I was to write this as a complete transfer system, I would write this as 3 on S, S plus 1, S plus 2, and then we're going to come to the denominator part, which I'm going to write in green, on 1 plus 3 on S, S plus 1, S plus 2. Now when you solve this equation, you will end up with 3 on S, S plus 1, S plus 2, plus 3 here. Now you can replace this whole system as this system: R of S coming in, C of S going out. Okay, this is all well and good, but if I was to give you this system and I was to say, hey, look, you're a smart guy or girl, and I want you to solve this in 2 seconds, well, you're gonna say, oh great, no. The reason being that now, to find the poles of the system, let's say if this exist, if the feedback wasn't there, then yeah, it would be really easy. You would just say, well, s equals 0 is one pole, s equals -1 is one pole, and s equals -2 is one pole. At that point, system just unstable, system goes to infinity. But now, you've got a term 3 here, and this is a cubic. Solving cubics and having this here doesn't make your life easy. So, what do? Well, there is this thing called, we have is sort of a theorem, a sort of a result or a rule or postulate, something like along those lines. I won't go into the technicality of things because a postulate is different to a theory, is different to a rule, and all sorts of things. What I will tell you is in layman's language is if your closed loop transfer function has only left half plane poles. So let me make a pole 0 plot here. So if this is your plot, and I'm going to choose the color black, so if your poles lie on the left hand side and only has left poles, then the factors of the denominator of closed loop system transfer function will be of the form s plus a I. Now what does this mean? What did I just say? Well, what I said was if you have a closed loop transfer function, which is what I showed you before. So if you have a system, so I'm just going to draw the system here, and an adder, and this here, 3 on s plus 1, s plus 2, feedback, and you're taking the output from here. So I'm just going to draw a little C of s, and this is your input R of s. This is your output coming out of here. Okay, now what you can say, okay, let's plot the poles here. So there's a pole there, 0. There's a pole at -1, so I'm going to call this -1, and don't forget about this. And and so let me just actually, so there's a pole at -1, and then there's a pole at -2. All these poles can be taken to be the left hand side. Okay, now this is okay if there's 0 here, so you can consider 0 doesn't bother us. But so this is on left hand side, then that means that the closed loop system transfer function, the function that we wrote down earlier, which was of the form 3 on s plus 1, s plus 2, plus 3. Now this is your closed loop transfer function, because closed loop system transfer function, because this function here represents this whole system. That is, I can write this system as this. I just want to reinforce these things in you, because subtleties, sometimes if I refer to this as a closed loop function or a forward function, then it confuses people. You need to be clear in your terminology, even when explaining other people, is that this here is a forward transfer function, this here is a feedback. Together they make a closed loop transfer function. That function can also be written as this. Okay, this is generally written from the formula that if you have g of s, this is your g of s, 3, in our case g of s is 3 on s plus 1, s plus 2, divided by 1 minus plus g of s times the feedback transfer function. Usually in some cases you might find 1 on s here, or 1 on s squared, 3 on s squared, 3 on s plus 1, or something in a transfer function. Well, you multiply that. In this case, our feedback is just 1. So that's why we multiplied 1, and that's how I came up with this. You can refer to certain textbooks or even online sources to find out how we come up with this. Nevertheless, what he's saying here is that what we know is that if we have a transfer function, a forward transfer function whose poles lie on the left hand side of your plane, then this is the left hand side. This here, let me just color it in. This here is the left hand side of your plane. Then you can say that this transfer function is represented by some constant k, which can be any factor. It could be 100. In this case, it's 3, divided by s plus a1, s plus a2, s plus a3, and so on all the way to s plus an. Okay, and one more technicality is that if we take the product of all of these factors, that is, if we take, oops, oh, I meant that to happen. If we take the product of s plus a, s plus a2, a1 here, s plus a3, s plus a4, and all the way down to s plus an, what do we get? Well, you will get a polynomial with positive coefficients. Or, yep, you will get a polynomial with positive coefficients. Now, that is all well and good, but how does that help us? Okay, now, once you've understood that, a sufficient condition for a system to not be stable, that is, a sufficient condition for a system to not be stable is if all the signs of coefficients of the denominator of the closed loop transfer function are not the same. So let's say we multiply all those numbers together, s plus a1, s plus a2, s plus a3, and all the way down to s plus an, which we don't know how many factors it has and how many. So let's say we get something like sn an plus an minus 1, s to the n minus 1 plus an minus 2, s to the n minus a minus 2, oh sorry, s to the a minus 2, all the way down to a1, sorry, a0, s to the power of 0. Okay, now let's go by the statement. This is a statement that I took from a book. Now I want to read. The good thing is you should get into a habit of analyzing statements inside the book. That way it really helps if you're studying data sheets, and that's what I find as well. Okay, so let's go turn by turn. A sufficient condition for a system to not be stable. So to not be stable, we have a condition. That condition is if signs of all coefficients. So what is the sign of an? Let's say an is positive. The sign of coefficient of an is positive. Let's say this is negative. Let's say this is some negative beta, some positive alpha, and negative gamma, I suppose. Yep, okay. It is if signs of all coefficients, so its sign is plus, negative, negative, of the closed loop transfer function are not the same. Since this plus is not equal to this coefficient sign minus, this minus is not equal to this coefficient sign plus, it is a sufficient condition that our system is unstable. That is what this whole thing is about. Now we can come to developing our Routh Hurwitz criteria. How does this Routh Hurwitz criteria work? Well, we'll discuss the how do we make this Routh Hurwitz table? Okay, to make a Routh Hurwitz table, we first get our transfer function. So what I'm going to do is make one with you for some transfer function. So let's clear this and let me give you a transfer function. So let's say we have r of s. So I'm going to iterate all those facts that we did before and go step by step. 1000. I like this example because it gives you all the technicalities in one place. So s plus 2, s plus 3, and s plus 5. S plus 3 and s plus 5. Let me just get my calculator open on the side. Okay, and we are ready to rock and roll. And it has a unity feedback, so I'm gonna call this c of s, that's our output, and oops, go here, minus feedback. Okay, so it's a negative feedback system. Now, as you remember, I told you that we can represent this system just by one transfer function, and that transfer function is going to be of the form. So here, this is our g of s. Our h of s is equal to minus 1. So let's use the formula, I suppose. You can say, and the transfer function will be given as total transfer function will be given of TSS is equal to g of s on 1 minus plus g of s h of s. Okay, Now let's solve that. What do we get? Well, it's 1000 divided by s plus 2, s plus 3, s plus 5. All of that is divided by 1 minus plus minus 1 and 1000 on s plus 2, s plus 3, s plus 5. Okay, well, that's all well and good now. Well, you will solve this. This shouldn't be too hard, and you will come up with this number, 1000 on s cubed. So I've got it solved here. So s cubed plus 10s squared plus 31s plus 1030. You're already thinking, oh my god, there's a 1000 there, there's a 10 here, there's a 31. I think 31 is a prime. Yeah, 31 is a prime. Yeah, 31 is a prime, and then 30 is here. This looks already like way too hard, man. This is just next level stuff. Don't worry. Now we can we just know that this whole system can be represented as just this transfer function and this output here. Okay, let's clear this up and get our Routh table on. So I'm going to write this transfer function so that we don't forget it. 1000 on s cubed, 10s squared plus 31s plus 1030. The way to make the Routh tables is, first we start at the highest power and we go down to the lowest power. So the highest power of s is s cubed. Alright. The second highest power is s squared. Alright. Let me just make a straight line. The next power of s is s to the power of 1. Sweet. And the next power of s is s to the power of 0. Okay. Key to remember is if you go up to the power of 3, so you go s3, s2, s1. Basically, number of columns is equal to number of rows minus 1. So how many rows do we have here? 1, 2, 3, 4. So number of columns will be 1, 2, and 3. Okay, so number of columns is number of rows minus 1. Alright. Now we start filling in these columns. So these columns is, so you take the first coefficient of s cubed, which is what, 1. Write that down. I'm going to write the coefficients in different color, make it easier to distinguish. So let's choose yellow. It's 1. Then we skip s squared. We go to 31. We skip the next number. Since there isn't anything, we just take 0. So this is your first key technicality. You don't see anything next, put a 0. You don't see. Let me reiterate that again. You start with 1. Then you skip 1, so we skip 10, we go to 31, we copy that down. Then we skip 1030, and then we don't have anything left, so we copy down a 0. Okay, now s squared. S squared, when it comes to s squared, the next term, we start with that first term we skipped. So we skip the first one, we start with 10. So this is always going to happen. So I just take it to be always start with the first skip term. So this is, in this case, it's 10. So you skip the first one, you start with the next 10. Skip 31, copy down the next. Is there anything next? No. Copy down 0. Now, when you're done, you're with your first 2 rows. Stop. Take a breather. And now we come to the more technical stuff. Now we come to the concept of calculating determinants. Okay, now this shouldn't be too hard because determinants of a square matrix is pretty easy to calculate, and it's all well and good. Okay, so I'm going to change color now. I'm going to change to green. Okay, now how do we, when all of these other terms will be filled in by determinants? Okay, I know it sounds a lot of work, especially considering there's a 1030 here. You're already thinking, no, God save me. But here comes the magic part. You can divide any row with a constant. That's right, you can divide any row with a constant, but that has to be a positive constant. So you cannot divide this whole row by -2. No, you cannot divide this whole row by 5. No, but you can divide this row by a positive 2. You can divide this row by a positive 5. You can divide this row with a positive 10. Since 10 looks pretty good, it gets rid of all the zeros and stuff. So what we can do is divide this row by a positive 10. So if I divide this by 10, I divide this by 10, I divide this by 10. What do we get? You get 1, you get 103, you get 0. Notice, since you can divide, you can also multiply because, so you can divide and multiply by positive coefficients only. Remember that. This is a key technicality which I won't go into this video, but there's a reason that you can only divide by positive numbers. Okay, now we're done with that. Let's start calculating our determinant for s to the power of 1 column. Now, let me just too big. Just go here and here. How do we calculate? Which terms do we take? The left hand side is always the first column of the previous 2 rows. So what terms are in the first column of the previous 2 rows? So this row and this row are my previous 2 rows because this is the row I'm filling in. So first column is 1 and a 1. So I'm going to copy these 2 terms down, 1 and a 1. However, it is the right hand column that changes every single time. The right hand column is always the elements of the column above and to right. So go above to right. What do we see? We see 31 and 103. So let's copy those terms down. And we divide by the term above. So in this case, that is 1. Okay? We always divide by the term above in the first row above, most left hand term, that's the term we divide by. So what does this give us? Well, this will give us, so when you calculate the determinant, and we always take the minus, so there's a minus sign here, and so that comes out to minus 72. So I'm going to write that in a different color. So this is minus 72. So this evaluates to minus 72. Now let's calculate the determinant of this term. So always put a minus sign to go. Okay, the terms here are, so left hand side column doesn't change, so that's always 1 and 1, so 1 from here, 1 from here. The left hand side is the left hand terms are always go to your previous 2 rows, look to your right, yay, 0 and 0, yippee. So copy those terms down, you divide them by this term here, always this term, the first row above, most left hand side column term. So that's 1, and this is easy, this evaluates to 0. Then again, okay, 1 and a 1, so 1 here, left hand column never changes. Okay, this is now technical. You go up, you look to your right, you're like, right, there's nothing there. What should I put there? Should I just put X? Should I put Y? No, it's easier than that. You just put 0. So put a 0 there, put a 0 here, and you divide by 1. And that is also very easy, so I'm just going to fill it in. This is 0, and this is also 0. Okay, now we are down to our last row. Now let's calculate the determinant. I'm going to use a blue color this time. Okay, so what do? We take the first 2 previous rows, so 1 and minus 72. Copy those 2 down. Let's not forget that we have a minus sign. Every single determinant has a minus sign in front. And we go above 2 rows. We look to your right. You look at 1, 0, 3 and 0. We copy those 2 down. We divide by minus 72. We always divide by the term above, minus 72. This evaluates to 103. Okay. Should I write this in different color? Yeah, why not? So this evaluates to 103. Okay. Now let's do this one. So you know your left hand column never changes. So first 2 previous rows, 1 minus 72. Previous 2 rows, and then go above, look to your right, 0 and a 0, divide by minus 72, and you get a 0. Let's do that again. You go above, you look to, you look left hand side never changes, so you go let's not forget a minus sign here, and there should be a minus sign here, 1 and a minus 72. And you go about, look to your right, there's nothing there, so you say, hey, that's easy, 0 and a 0. You divide by minus 72 and you get a 0. So this here, ladies and gentlemen, is your Routh table. If I was to write it more clearly, this is what it will look like. 3 columns, which is always 1, so number of rows minus 1. So s to the power of 3. We start with our highest power, 2, s power of 1, s to power of 0. Then we, let's change color, we write down the coefficients of each of these terms. So you start with the 1, which is the coefficient of s to the cubed. Then we skip 10, we write down 31. Then we skip 1030, and we don't have any term next, so we just write down 0. Then we for the next row, we skip the first term, we write down the next term, 10. We skip 31, we write down 1030, and then since it's nothing there, we fill it in with 0. But seeing that these numbers are too big, we know that we can divide these numbers or multiply these numbers by any positive number. So in this case, I chose to divide by a 10, 10, and a 10. Notice you have to divide every single element in the row, otherwise this doesn't work and this is totally wrong. What you get is you get 1, you get 103 here, and you get 0 here. Then you take the determinant, which is always minus determinant, and you take the first two. So the left hand side is always the previous 2 columns. So you look at the previous 2 rows, and you copy their numbers there. So in this previous 2 rows, there's 1 and minus 1. Now this doesn't change for any single block here, but the right hand side is the what varies. So you go up, you look to your right, you see 31 and 103. You copy those down. Then you come here and you divide this by 1. That is this element here. The left hand side never changes, 1 and a 1. So don't forget the minus sign. You go up, look to your right, there's a 0 and a 0, and you divide by 1. So this is how you can fill out the whole Routh table. Now in my next video, we will learn how to analyze it and how to determine stability criteria and stuff. Just so you know, this table tells us about the number of poles on the left side, number of poles on the right side, and number of poles on the imaginary axis. So I hope you had fun, and hopefully you understood something, and I will see you in the next video. Take care.